yeah, so the speaker, as you can see, is Kashif Nawaz in this joint work talking about HQC again. Please, Kashif, thank you.
Thank you, John Christoph. Thank you, Eduardo. So the topic for this presentation is automating cryptographic hardware implementations in the case of HQC. This is a joint work by Carlos Aguilar, John Christoph, Arnaud, Roma, Vincent, Mamuri, and myself. So very briefly,
we stopped hearing you.
Sorry for that. There seems to be the slide which is still working. I will just remove the audio from the slides.
Okay. This stuff happens.
So in this talk, we will briefly provide a motivation for HLS, why high-level synthesis is required, our contributions, results, and key takeaways. Now, high-level synthesis has been touted as replacing digital designers.
Kashif,
yes.
We do not see your slides. I think you need to share the screen again. Okay.
So high-level synthesis has been touted as replacing digital designers since quite a long time. The community is very active in developing newer tools which are able to synthesize the original code. In this case, the original refers to the existing software implementation, C, C++, or even System C. Once the code is ready and it has been validated, the C-level functionality is clear, then it is passed to a synthesizable engine which creates an HLS model. Now, the HLS model first ensures that the functionality is maintained. This is kind of similar to a formal verification step wherein the code functionality remains the same, but then the blocks and the wires and the other registers are kind of being inserted to check whether the design still passes the golden reference. After this, it is possible to go for further optimization in which the code is restructured. Optimizations in case of HLS include loop unrolling, loop pipelining. These are different mechanisms. We will not go into the details, but which allow for the HLS code to be made more generic and faster. Also, HLS offers the additional possibility of adding directives and constraints. This is very helpful from a C or a software level programmer's perspective, as it allows them to operate on pragmas and other directives trying to control the different blocks. So it is possible that the software developer can choose not to optimize a further block, set it to a don't touch condition, whereas just optimize a particular some other block. Once the HLS model is in a format ready to be synthesized, it is passed to the HLS tool where a functionally correct RTL is generated. This is, of course, verified by a co-simulation with a test bench, and the RTL functional verification has the same test suite as was present in the original C level. The pros and cons for HLS from this are that HLS allows for rapid prototyping. It allows the software level code to be very quickly translated into RTL development. It speeds up the process, but the problem occasionally which RTL developers face while reading such code is the non-human readability format. the names of the registers, for instance, or the nets are generally not very easy to are not something which the RTL developers are more accustomed. And it is also possible that tracing back from the from the RTL to the C is kind of difficult, because HLS the HLS compiler tends to create different uh, tends to create multiple instances of the same block, so that whenever there is a function call, it creates multiple such instances, and then going back to which one exactly is being called kind of takes some time. But HLS also allows us to catch certain bugs early in the design. It reduces the effort for RTL verification. And as we'll show, for critical bottleneck functions, this is something which is quite useful. The current state of the art, the motivation for driving HLS into an open source framework is currently underway, especially in the areas of neural network architectures. We see a lot of open source libraries being developed, and HLS is being leveraged to use the power of parallelization of FPGAs for this. The one of the key advantages is that it allows platform independent code from software developers. As long as the code compiles functionally correctly and is giving the desired output, it is possible to convert that code into a high level synthesizable RTL flow. Generally speaking, higher the abstraction level, the better it is for the HLS tool. And there is also development of independent HLS libraries, which is kind of similar to the open source software libraries we have today. But in addition to all of this, we have the leading market vendors who have their own state-of-the-art HLS tools available from Xilinx, Microsemi, as well as Intel. For this work, we used the Xilinx tools, the HLS compilers from them. A good work which covers the existing state of the art in very good details is this work from Numan et al., an extensive coverage of the various existing tool chains and the comparisons. This work compares the different HLS compilers and tools which are currently available and provides a nice comparison between them. So in the case of HQC, which is our target cryptographic algorithm and one of the alternate candidates for the final NIST PQC round, we choose the multiplier adder module for the polynomial multiplication and the shake, which is used in the random generation. Now, these two functions have been shown to be critically important. They form the core bottlenecks because of their long critical paths. And we wanted to understand how the HLS tools can be used to better optimize and make these paths more efficient. For the purposes of our ongoing work, we developed two versions known as compact and perf, which is for the performance version. And in additionally, we developed a pure HLS flow in which the C code is directly synthesized into an RTL Verilog, and an optimized HLS flow in which the synthesizable Verilog or the VHDL is then manually refactored to remove some of the redundancies. So this is something which I mentioned earlier, that HLS tends to create multiple instances of the same, let's say, for example, the Ketchup module, and then calls each of them separately. This is, of course, may be beneficial from a software point of perspective, but from hardware, it just wastes resources. So to optimize it, we just keep one of the Ketchup modules, and this version we refer to as the optimized one. These are some very initial results from the HLS of the multiplier adder module. We increase the size of the multiplier bit width from 8 to 256, but for the purposes of just showing here, we'll just stick to these three. As expected, the number of LUTs, which is the area, will increase The registers is also expected to increase in this. The maximum frequency achieved is a bit impressive, given that that not much optimizations were made on this. The overall latency goes down both in terms of cycle and the time of computation required. And the area latency product, which is a measure of how good or bad an implementation is, also goes down with increasing the width. Moving on to the Ketchuk F1600 module, we compare this with one of the state-of-the-art referenced as the number 5 here. As we can see, there is a reduction of around 40 times in the number of total clock cycles at the cost of similarly placed registers. In terms of the total area, we optimize by a factor of 2, which allows that the HLS optimizes definitely in the correct direction. Additionally, it also allows target frequencies of up to 200 megahertz for the Ketchuk module, given that the module itself has a very long critical path. Achieving 200 megahertz is quite credible, although a manually crafted RTL could exceed this. So in conclusion, we would like mention that although HLS is not quite there yet, but it is gaining some good attention in the hardware software design community. It's possible that for rapid prototyping of co-design based systems, especially in the case of NIST PQC candidates, which we see HLS could be useful. And also for estimating some preliminary results. In fact, some of the first works, which was done like a comprehensive survey on most of these candidates around 2018 probably, was done using HLS. In critical bottleneck functions, HLS allows hardware software developers to quickly optimize, make changes to their code, and they can easily get back, rather than in the case of in case of a full RTL development, where it is often time consuming, and certain bugs, if caught at the very end, lead to a complete change of the system. At this point, we would like to stress that HLS can never replace handcrafted RTL. It is not going to completely throw digital designers out of business. Rather, it would complement it, especially for quicker and getting more cheaper results. And as design automation tools evolve for security, and as artificial intelligence makes its way into the a lot of products from the EDA community, HLS could benefit from such increased convergences. It is equally possible that the new tools which we will have and in fact one of the leading market vendors have come up with an AI-based HLS tool, which promises to be much more closer to a handcrafted RTL design. These are the references which were used, and thank you for listening to my presentation.
Thank you, Kashif. I don't know if we have questions for you. I will try to keep on reading. Yes, question from Andrea, who wants to speak one.
So I'm not a hardware or software developer, but the slide that mentions that HLS could help them make optimizations or changes. Is there anything in there that would prevent them from making changes that actually jeopardize the security of the scheme itself?
I'm sorry, can somebody, I heard part of the question where HLS kind of jeopardizes the security. Which slide were you referring to, please?
You may have to come up and repeat the question.
Hi, I was wondering about this slide about HLS can help hardware and software developers make optimizations or changes. And I'm wondering, is there anything in there that would prevent them? Because, right, sometimes people make optimizations that actually jeopardize security. Are there any safeguards against that, or?
Okay, yeah, I got your question. Thank you. Well, actually, to be honest, till now, even with handcrafted or pure RTL development, I see that we have not achieved that same level of conviction that we can say that the RTL code is secure. And there are a lot of tools, both commercial as well as academic, which are able to find such loopholes, if you would say, in the design. And these are often the reasons for the microarchitectural leaks. Not speaking of side channels, because side channels is kind of more physical, but from architecture point of view, yes, it is possible. So regarding HLS, it would be kind of too, I would say, too early to say that. Right now, given the EDA community, especially these leading market vendors, are very much focused on performance. So I think we would need some time. Maybe if we have more open source such tools available, which drive towards having more security. For instance, if there is a possibility of including the different common vulnerabilities, the CVE, the MIT, RE vulnerabilities, which are generally used in software as well as hardware, into such designs, it could be a good start. I hope that answers your question.
Yes, thank you.
Thank you.
Okay, if it's easy, I can repeat it. Otherwise, you can come up.
Slide 17. What is the red one? The clock cycle. What are the other clock cycles for the catch-up? Like here. And what do you compare here? Clock cycle for catch-up and catch-up for HLS? And is the catch-up then implemented with Verilog, or what are clock cycles?
Well, yes. Actually, it's for the sorry, it's for the Shake module. Yeah, it's for the Shake 256, which uses the Ketchup F1600.
But what are the clock cycles on the red chart? Like, is it implemented in C code and then boil it down? And how do you count the clock cycle for the red?
The value, for instance, this 151, which we achieve here, is from the C code translated HLS, and this was after running a simulation. So we do not take in. So if you are saying about the synthesis tool, which gives a whole range of values, no, we do not take into account that, because that is for the. It's like for the complete case, but for the most accurate representation, we use the simulated values.
Different one for my question, like in the red part, like I understand the HLS part, so you took secret and transferred it to the first one. And the red, how do you?
The red value is from the paper, so it's from the reference. Yeah, sorry, it's missing on the other one, but it's here. It's from this reference paper which we took this value from.
Okay.
Sorry, it got missed on the other slide. Yes.
Yeah, it was not clear that the 5 there is the reference.
Yeah, it didn't get copied to the other one. Sorry for that.
It's okay. That's clear. That's why we asked the question.
Can you show the reference again?
Oops.
Thank you.
Thank you.
Do we have more questions for Kashif? No? Okay, so I would like to thank you again for the talk.
Thank you.